Hello everyone. So today I'll be talking about Helly's theorem in this video. Let's look at the statement. So the statement says that we have n entities which are finite collection of convex subset which belong to dimension d in real space, and n can be greater than equal to d plus 1 d. This d is same as the dimension. Now it is given that the intersection of every d plus 1 sets is non-empty, and we need to prove that the intersection of all these sets in this finite collection is non-empty. So let's try to write it in a mathematical notation what is given and what we have to prove to just make things better, like to make things clear. So let's say this is L, and L is such that it is intersection of I equals to 1 to, let's say, d plus 1 of all the xi's, and it is not empty. It's given. So this is equivalent to, there is some v1 which belongs to this L, right? So this is already given, and we need to prove, given this fact, that there is a k which is, let's say, intersection of all the n subsets. Okay, again, which is non-empty, which is equivalent to there exists, let's say, this v which belongs to this convex subset. Okay, so this is given, and we need to prove this. Okay, so yeah, let's take a look at the proof. For R2, it is quite trivial. So when dimension is 2, you're going to have d plus 1 sets. So you're going to have 3 sets. And it's already given that the d plus 1 sets will intersect. So yes, they'll have a point of intersection, as I have explained here, as I've drawn here. Okay, let's take a look at a more complicated situation when we have 4 sets. In this case, there are going to be 2 representations of convex hull, right? So in this case, it's quite clear that V4 will be the point of intersection. Okay, so this case is just done. Let's take a look at this case. Okay, and so I made a construction something like we have an element from each set because all 3 intersect, right? So let the construction be like this, that the element is represented by the subsection I of which it does not belong to. Okay, so I have a V1 such that it belongs to X2 intersection X3 intersection X4. Similarly, V2, V3 and V4. Now I have a common point of intersection for V1, that is, it belongs to X2 intersection X4, as well as V3 belongs to X2 intersection X4. Similarly, V2 and V4 belong to the same intersection. So since it belongs to the same intersection, we can say that it belongs to the convex hull of that intersection, right? Okay, now we just need to apply Radon's theorem. A quick note, if you don't know Radon's theorem, please go and watch my previous video and you'll understand better. So if you use Radon's theorem, you already have that the V is convex hull of 2 partition set. So V is going to be the convex, V is going to belong to the convex hull of all of them. So it is going to be convex hull of V1, intersection V2, intersection V3, intersection V4. Okay. Okay, now let's take a look at when we have such n cases. Now we just worked for our 3, right? Now let's say we have n cases. So what is going to happen in n cases? Let's try to analyze. So here, I'll just write this thing again. So for V4, I'm going to write, no, let's just try to write for VI. For VI, I'm going to write that intersection xi plus 1 intersection x n, right? So I doesn't belong to the element itself. So vi does not belong to xi. This is our construction and it belongs to the rest all. Okay. So we are going to have, so it doesn't really make any difference. You see, it's the same construction as this. And now instead of this, we'll have till xn. Same goes here. And now then we'll have convex hull of x1 intersection x2. Oh, sorry. No, x2, x3, and so on till xn, where we won't have I. This will be the convex hull. Yes. So this is for the n cases. Now let's try to analyze when our n will be greater than d plus 2. Okay. So when our n is, so what this is basically you, okay. Yeah, this is okay. This is okay. Okay, you have such many sets, okay? And there is a point of intersection between every three, and there is a point that belongs in the intersection of all the convex sets. So now, let's say we have been added with one more d plus 2 set. Okay, so this is one more d plus 2 set. Let's say this is d plus 2 set. Okay, so this I'm just going to consider as one set now, which is x d plus 1. So yes, this is going to be my new single set instead of this one. So now I'm not working with just this one, but I'm working with this, both of them, right, as a single set. So whenever you'll have something greater than d plus 2, you'll just combine it, you'll take the intersection of it and you'll work on it. So we had our base case, we had our inductive step, and this is how we can prove Helly's theorem by induction. So if you have any questions, let me know. Thank you so much for watching the video and goodbye.